Picture this: a single spot on the surface of the Sun, so unimaginably hot that it could melt solid steel in seconds, turning it into a glowing, liquid stream. Now zoom out, way out, until that blazing star is just a tiny speck in the endless black ocean of space. Out there, beyond the fiery fury of stars, lies a universe of extremes, places where heat and cold defy everything we know, where temperatures soar and plunge to limits that seem almost supernatural. Have you ever wondered just how hot or how cold the cosmos can get? What if I told you there are places where matter is crushed into a state hotter than the core of a supernova, or stretches of emptiness so cold that atoms nearly stop moving altogether? This is a journey to the edges of what's possible, where the laws of physics twist and bend under the weight of these incredible extremes. We're talking about neutron stars, where a teaspoon of material weighs 1 billion tons and burns at 1,000,000 degrees, or the vast voids between galaxies, where temperatures plunge so low they're just fractions of a degree above absolute zero. These aren't just numbers on a scale, they're windows into the universe's most violent and serene corners, where heat and cold shape the fate of stars, planets, and even time itself. And today, we're diving deep into 30 of the most astonishing, mind-bending facts about these extremes, facts that will challenge everything you thought you knew about temperature. From the searing furnaces of colliding stars to the eerie, frozen wastelands of deep space, each one reveals a universe far stranger and more spectacular than we could ever imagine. So buckle up, because by the time we're done, you'll never look at a sunny day or a cold night the same way again. The cosmos is about to show you what it truly means to be extreme. At the heart of our solar system, buried beneath thousands of kilometers of swirling plasma, lies a natural fusion reactor so powerful it defies comprehension: the core of the Sun. Here, temperatures soar to an unimaginable 15 million degrees Celsius, a heat so intense it could vaporize every human-made structure on Earth in an instant. This isn't just heat, it's the engine of creation itself. Under these extreme conditions, hydrogen atoms, squeezed by the crushing gravity of the Sun's mass, collide with such force that they fuse into helium, releasing energy in a process that has burned non-stop for over 4.6 billion years. To put that into perspective, picture the hottest lava on Earth, a searing river of molten rock at around 1,200 degrees Celsius, hot enough to melt steel. Now imagine something 12,500 times hotter. That's the Sun's core. Yet this staggering heat isn't just a cosmic curiosity, it's the reason we exist. The energy released from these fusion reactions travels outward as light and heat, taking hundreds of thousands of years to reach the Sun's surface, then just 8 minutes to cross the void and warm our planet. Without this relentless furnace, Earth would be a frozen, lifeless rock, drifting in perpetual darkness. But here's what's truly mind-blowing: even this inconceivable heat is just the beginning. Elsewhere in the universe, temperatures climb to levels that make the Sun's core seem almost mild. Yet none of those extremes would matter if not for this golden ball of fire, quietly converting millions of tons of hydrogen into helium every second, proving that sometimes the most extreme places in the cosmos are also the most life-giving. The Sun isn't just a steady ball of fire. It's a raging, unpredictable beast capable of throwing cosmic tantrums so violent they'd make any earthly volcano seem like a candle flame. When solar flares erupt, they unleash temperatures close to 10 million degrees Celsius, nearly as hot as the Sun's core itself. These explosions aren't just visually spectacular, they're raw demonstrations of the Sun's magnetic field snapping like an overstretched rubber band, releasing enough energy in minutes to power human civilization for thousands of years. Picture this: a tangled knot of magnetic energy suddenly breaks free, accelerating charged particles to nearly light speed while superheating surrounding plasma. The result, a brilliant flash visible across the solar system, followed by an avalanche of X-rays and extreme ultraviolet radiation. This violent energy surge can reach Earth in just 8 minutes, bombarding our upper atmosphere with enough force to disrupt radio communications and fry sensitive satellite electronics. One particularly powerful flare in 2003 was so intense it temporarily blinded several scientific spacecraft and forced astronauts on the International Space Station to take shelter. But there's beauty in this chaos. Those same particles that threaten technology also create nature's most dazzling light show, the auroras. When a solar flare's charged particles collide with Earth's magnetic field, they're funneled toward the poles, setting the sky ablaze with shimmering green and purple curtains. The stronger the flare, the further south these northern and southern lights can be seen. Ancient civilizations thought they were spirits dancing. Today we know they're visual proof of our planet's magnetic shield bending under the assault of a star's fury. Yet the real danger comes days later, when the slower-moving cloud of plasma from the flare arrives, triggering geomagnetic storms powerful enough to induce electric currents in power lines. In 1989, one such storm left 6 million people in Quebec without electricity for 9 hours. Scientists warn that an extreme solar storm today could cripple global grids for months. It's a humbling reminder that even from 150 million kilometers away, the sun's tantrums can reach out and touch us with devastating consequences. If you think Earth's lightning is intense, wait until you hear what happens on our so-called twin planet, Venus. Here, bolts of lightning don't just crackle. They supercharge the atmosphere to a staggering 30,000 degrees Celsius, 5 times hotter than anything we experience on Earth. That's hot enough to instantly vaporize metals like iron and turn sand into glass. And unlike our planet, where lightning dances between clouds or strikes the ground, Venus's lightning tears through an atmosphere so thick it would crush you like a soda can, a toxic, swirling soup of carbon dioxide laced with sulfuric acid clouds. What makes Venus's lightning so extreme? It all comes down to that suffocating atmosphere. While Earth storms form from water vapor rising into relatively thin air, Venus's weather is fueled by heat trapped under a blanket of greenhouse gases. The planet's surface bakes at 460 degrees Celsius, hot enough to melt lead, while hurricane-force winds whip acidic clouds around the planet faster than Venus itself rotates. When electrical charges build up in this hellish environment, the resulting lightning isn't just powerful, it's relentless. Some scientists estimate Venus may have twice as much lightning as Earth, with bolts crackling non-stop in its permanent twilight, unseen beneath those opaque yellow clouds. But here's the twist: we've never actually photographed a lightning bolt on Venus. Instead, spacecraft like the European Space Agency's Venus Express have detected the unmistakable radio crackles of electrical discharges. These findings are more than just trivia. They help scientists unravel why two similar-sized planets ended up with such wildly different climates. Some researchers even suspect Venus's lightning might be creating bizarre chemical reactions in its clouds, potentially sparking molecules that could, in theory, hint at how life might emerge in the most hostile environments. So while we'll never walk on Venus's scorching surface, its furious storms are sending us signals, teaching us just how alien and extreme a planet's weather can become. A supernova isn't just a star dying, it's a star rewriting the very fabric of the universe in a single, cataclysmic tantrum. At the moment of explosion, temperatures inside the collapsing core spike to an incomprehensible 100 billion degrees Celsius, hotter than anything else we've observed in nature. That's not just heat, it's a cosmic forge so intense it warps the laws of physics, fusing atoms with such violence that it creates elements heavier than iron, including the gold in your jewelry and the uranium powering nuclear reactors. Imagine the crushing weight of an entire star's worth of matter collapsing inward at a quarter the speed of light, only to rebound in a shockwave that rips the star apart. The energy released in that instant outshines an entire galaxy of stars for weeks, blasting stellar debris across space at millions of kilometers per hour. Within that expanding cloud of superheated gas, the extreme pressures and temperatures force atomic nuclei to fuse into forms that normal stellar fusion could never produce. Every platinum ring, every titanium hip replacement, even the iodine in your thyroid, they were all forged in these apocalyptic explosions billions of years ago. Here's what's truly humbling. We're literally made of stardust. Without supernova scattering these heavy elements across the galaxy, planets like Earth would never have formed, and life as we know it wouldn't exist. That dying star's final act, a brief, unimaginably violent flash, became the reason you can hold a piece of metal in your hand that was born in the heart of a cosmic detonation. And somewhere out there, right now, another star is reaching the end of its life, preparing to ignite a chain reaction that will seed future solar systems with the building blocks of new worlds. After the cataclysmic fury of a supernova comes something even stranger, a cosmic zombie, the stellar corpse known as a neutron star. Imagine taking the entire mass of our sun and crushing it down into a sphere no wider than Manhattan. The result is an object so dense that a single sugar cube-sized piece would weigh 1 billion tons, more than all the cars on Earth combined. But it's not just the density that boggles the mind. The surface of these collapsed stars burns at a constant 1 million degrees Celsius, glowing with an eerie blue-white heat that defies earthly comparisons. How does something so small stay so blisteringly hot? The answer lies in its violent birth. When a massive star collapses, the protons and electrons in its core get squeezed together with such force that they merge into neutrons, releasing a flood of energy that keeps the neutron star's surface white-hot for billions of years. Unlike ordinary stars that generate heat through fusion, these remnants are kept hot by the sheer pressure of their own gravity, so strong that if you dropped a marshmallow onto its surface, the impact would release as much energy as a nuclear bomb. Yet neutron stars aren't just cosmic curiosities, they're laboratories for extreme physics. Their crushing gravity warps space-time so dramatically that they serve as natural proving grounds for Einstein's theory of relativity. Some neutron stars, locked in deadly dances with companion stars, emit regular pulses of radiation as they spin hundreds of times per second, acting as cosmic lighthouses that help astronomers map the universe. And when two of them collide, the resulting gravitational waves ripple through space-time itself, shaking the very fabric of reality. These collisions are so violent that they forge gold, platinum, and other heavy elements, scattering them across the cosmos like celestial treasure. So while neutron stars may be the remnants of dead stars, they're far from lifeless. They're cosmic powerhouses, rewriting the rules of physics while glowing with heat that would vaporize any known material in an instant. The universe has a way of turning destruction into something dazzling. There's a place in space where temperatures make supernovas seem almost lukewarm, a swirling storm of subatomic particles called the Crab Nebula's pulsar wind. At its heart lies a spinning neutron star, firing a jet of charged particles so violently that plasma in its wake heats to an almost incomprehensible 10 trillion degrees Celsius. That's not just hot, it's 1 million times hotter than the core of the sun, a fleeting glimpse into conditions so extreme they haven't existed since the first trillionth of a second after the Big Bang. This cosmic furnace works like nature's own particle accelerator. As the pulsar spins 30 times a second, its crushing magnetic field whips electrons and protons to near light speed, sending them screaming outward in a hurricane of energy. When these particles collide with slower moving gas in the nebula, the impact converts their motion into pure heat, so much heat that if you could bottle even a speck of it, it would vaporize our entire solar system instantly. But here's the twist: this isn't random chaos. The pulsar's wind organizes itself into eerie, glowing filaments, sculpted by magnetic fields into patterns that stretch light years across space. To put this temperature into perspective, consider humanity's most powerful particle smasher, the Large Hadron Collider. When it smashes protons together, it can briefly generate temperatures 100,000 times hotter than the Sun's core. Yet even that pales next to the Crab Nebula's natural furnace, which operates at scales we can't hope to replicate. What's truly mind-bending is that this isn't some rare phenomenon. Every pulsar in the universe likely creates similar conditions, turning the corpses of dead stars into engines of unimaginable heat. And here's the kicker, we can actually see this process in action. The Crab Nebula's pulsar wind glows in X-rays so intense they pierce through cosmic dust, allowing telescopes to map its structure in vivid detail. It's a reminder that the universe doesn't just contain extreme temperatures, it thrives on them, using these unimaginable energies to sculpt the very fabric of space itself. So the next time you feel a summer day is too hot, just remember, out there in the heart of a shattered star, particles are dancing at temperatures that make our sun's core feel like a cool breeze. Deep in the hearts of distant galaxies, monsters lurk, supermassive black holes so powerful they can heat matter to 10 billion degrees Celsius as they devour it. These aren't just any cosmic ovens, they're quasars, the brightest objects in the universe, fueled by black holes billions of times heavier than our sun. Picture a whirlpool of gas and dust spiraling toward an invisible point of no return, moving so fast that friction alone heats it to temperatures rivaling the first moments after the Big Bang. The energy released is so intense that it shoots out in jets stretching hundreds of thousands of light years, piercing through galaxies like cosmic blowtorches. What makes these jets so unimaginably hot? It's all about physics pushed to the breaking point. As matter falls toward the black hole, it doesn't just plunge straight in. It forms a swirling disk spinning at nearly light speed. The particles in this disk smash together with such violence that they emit X-rays and gamma rays, turning the region around the black hole into a natural particle accelerator. Some of this superheated plasma gets funneled by the black hole's twisted magnetic fields and launched into space at almost the speed of light, creating jets that glow with the heat of 10 billion suns. These aren't gentle streams, they're raging rivers of energy capable of sterilizing entire galaxies in their path. The truly wild part, we're essentially looking back in time when we observe quasars. The light from the most distant ones has traveled for billions of years, meaning we're seeing the universe in its violent infancy, when black holes feasted freely on dense gas clouds. In a way, quasars are cosmic fossils, preserving the extreme conditions of the early universe, conditions so hot and dense that matter behaved in ways we can barely simulate with our most powerful supercomputers. Some scientists even think these jets played a crucial role in shaping the cosmos, heating surrounding gas so much that it prevented small galaxies from forming too early in certain regions. Modern telescopes have given us front-row seats to this spectacle. Simulations show glowing tendrils of plasma twisting like spaghetti in a black hole's gravity, then suddenly being hurled outward in narrow beams. Real observations match these models almost perfectly, capturing jets punching through intergalactic space, leaving behind bubbles of radio emission visible across cosmic distances. It's humbling to realize that the same forces heating your morning coffee, friction and motion scaled up to cosmic proportions, can create some of the most extreme temperatures in existence. And somewhere out there, right now, another quasar is likely waking up, preparing to unleash a jet that will outshine its host galaxy for millennia to come. Death Valley isn't just hot, it's a blistering anomaly that defies our understanding of survivable conditions. In 1913, this sun-scorched basin in California shattered records with a staggering 56.7 degrees Celsius, a temperature so extreme it could fry an egg on the sidewalk in minutes. But this isn't just about numbers on a thermometer. Imagine standing on cracked Earth so parched it looks like a shattered mirror, where the air shimmers with heat waves strong enough to distort the horizon. At these temperatures, metal car door handles become searing traps, and even shade offers little relief when the ground itself radiates like a furnace. What makes Death Valley the hottest place on Earth? It's a perfect storm of geography and physics. Nestled 282 feet below sea level, the valley acts like a natural convection oven. Its steep mountain walls trap hot air, while the dark desert floor absorbs nearly all incoming sunlight, converting it into relentless heat. When winds sweep down from surrounding peaks, they compress and heat up further, creating gusts that feel like a hairdryer set to maximum. Scientists call this the downslope wind effect, and in Death Valley, it can turn already scorching days into infernos. Yet life persists even here. Tiny creatures have evolved mind-bending survival strategies. The Death Valley pupfish thrives in springs barely cooler than the surrounding desert, while microscopic extremophile bacteria flourish in salt flats that would boil an ordinary cell alive. These organisms produce special heat shock proteins that prevent their DNA from unraveling, like microscopic air conditioning units. Even the rocks participate in this extreme ballet, expanding in the day's heat with audible pops and cracks before contracting again under the cold desert night. But here's what's truly unsettling. Death Valley's record may not hold forever. In 2020 and 2021, satellites detected ground temperatures here approaching 81 degrees Celsius, hot enough to cause third-degree burns on contact. While these readings don't count as official air temperatures, they hint at a frightening trend. As climate change intensifies, this natural laboratory of extremes may soon rewrite the rules of what we consider possible on our own planet. The cracked Earth tells a story not just of an inhospitable desert, but of a world constantly pushing the boundaries of heat beyond what we once thought imaginable. Venus isn't just hot, it's a planetary pressure cooker where temperatures stay high enough to melt lead around the clock every single day of its year. At 465 degrees Celsius, the surface is so scorching that even metals like bismuth and cadmium pool into shimmering puddles across its volcanic plains. But here's the cosmic irony. While the ground bakes under this perpetual heat dome, the upper atmosphere 60 kilometers up shivers at a frosty -40 degrees, with clouds of sulfuric acid ice crystals floating through skies thinner than Earth's highest mountains. This bizarre split personality makes Venus the solar system's ultimate study in extremes. The culprit behind this hellish environment, a runaway greenhouse effect gone berserk. Billions of years ago, Venus might have had oceans like Earth, but as the young sun grew brighter, those waters evaporated, pumping massive amounts of water vapor, a potent greenhouse gas, into the atmosphere. Without oceans to absorb carbon dioxide through natural cycles, the gas built up uncontrollably. Today, Venus's air is 96% carbon dioxide, with an atmospheric pressure 92 times heavier than Earth's at sea level. This thick blanket traps heat so efficiently that the surface stays hotter than Mercury, despite being nearly twice as far from the Sun. The result is a world where the very rocks glow faintly red at night, radiating trapped heat like coals in a furnace. Humanity's attempts to explore this inferno read like a horror story of melting machinery. The Soviet Union's Venera landers in the 1970s and 80s were engineering marvels designed to withstand extremes no earthly environment could match. Venera 13, the most successful, transmitted color photos for a heroic 127 minutes before succumbing to the heat. Its titanium hull slowly baked, its lenses cracked under atmospheric pressure equivalent to being 900 meters underwater on Earth, and its electronics fried despite triple-layered insulation. Earlier probes like Venera 7 fared worse. Its parachute melted during descent, sending it crashing into the surface where it lasted barely 23 minutes. Yet these short-lived missions revolutionized our understanding. Venera's cameras revealed a landscape of cracked basalt under an orange sky, where sunlight diffuses so thoroughly that shadows barely exist. Modern radar mapping shows entire mountain ranges forged from metal-rich minerals that would instantly deform under Earth's gentler conditions. Some scientists speculate that Venus's highlands might even host exotic snows of lead and bismuth compounds that vaporize before reaching the lower plains. Perhaps most fascinating is what Venus teaches us about climate extremes. The same greenhouse processes trapping heat that operate on Earth, just at a smaller scale. Venus stands as a cautionary tale written across an entire planet, showing what happens when balancing systems fail. Its upper clouds, oddly enough, have recently revealed potential signs of phosphine gas, a possible biomarker, suggesting that even in this hellscape, nature might find ways to persist. Whether that's true or not, Venus remains the solar system's ultimate lesson in how delicate the line between habitable and hostile can be. A world where the air is thick enough to swim through, the rain burns like acid, and the ground glows with the heat of a self-made oven. Jupiter's moon Io doesn't just have volcanoes, it's a celestial pressure cooker where the very ground beneath your feet would be liquid. A world so geologically hyperactive it makes Earth's most violent eruptions look like gentle bubbles in a simmering pot. Here, lava lakes sprawl across the surface like boiling cauldrons, reaching temperatures of 1,300 degrees Celsius, so hot they glow with an eerie incandescence even in full sunlight. This isn't just molten rock, it's liquid fire so scorching that if you could stand on Io's surface, which you absolutely couldn't, the radiant heat alone would vaporize your spacesuit before you took a single step. What fuels this apocalyptic landscape? The answer lies in Jupiter's crushing gravity. Io orbits so close to the gas giant that the planet's gravitational pull stretches and squeezes the moon like a cosmic stress ball. This constant kneading, called tidal heating, generates so much internal friction that Io's core stays perpetually molten, forcing vast quantities of magma up through hundreds of active vents. NASA Galileo spacecraft captured this pandemonium in stunning detail: fountains of lava shooting 80 kilometers above the surface, plumes of sulfur dioxide gas painting the sky yellow, and lakes of liquid rock larger than entire cities bubbling violently underfoot. One particularly dramatic eruption in 2001 produced a lava flow over 500 kilometers long, enough to stretch from New York City to Washington, D.C., with enough molten rock left over to bury Manhattan under 30 meters of lava. Comparing Io's volcanoes to Earth's is like matching a birthday candle against a flamethrower. While our planet's mightiest eruptions like Mount St. Helens or Krakatoa might blast cubic kilometers of material into the atmosphere, Io's average daily output dwarfs them combined. Its most powerful eruptions eject material at velocities nearing 1 kilometer per second, sending volcanic debris into orbit around Jupiter itself. The composition differs too. Earth's lava is mostly silica-rich basalt, while Io's is likely hotter, runnier ultramafic lava packed with magnesium and iron, giving it that surreal orange glow visible from space. Yet for all its fury, Io offers scientists a priceless natural laboratory. By studying its extreme volcanism, we gain insights into how tidal forces shape worlds across the galaxy, including distant exoplanets orbiting close to their stars. Some researchers even speculate that early Earth might have gone through a similar hypervolcanic phase, with tidal forces from the young moon triggering global eruptions that influenced our planet's early atmosphere. Every plume we observe on Io isn't just a spectacle, it's a window into planetary evolution at its most extreme, a reminder that even in the cold depths of space, heat can reshape worlds in ways we're only beginning to understand. At the opposite end of the cosmic temperature scale, from searing stellar furnaces, lies the most elusive chill of all: absolute zero. The theoretical temperature where all molecular motion stops completely, minus 273.15 degrees Celsius, is more than just a number on a thermometer. It represents the ultimate limit of cold, a frontier that has taunted scientists for over a century. While the universe naturally dips close to this extreme in the vast voids between galaxies hovering just 2.7 degrees above absolute zero, human laboratories have gotten far closer, manipulating individual atoms with lasers and magnetic fields to reach temperatures within a billionth of a degree of this impossible chill. Reaching these extremes isn't just about breaking records, it reveals a bizarre quantum world where matter loses all familiarity. At a few billionths of a degree above absolute zero, atoms slow down so dramatically that their wave-like nature takes over, merging into a single quantum entity called a Bose-Einstein condensate. Picture an entire cloud of atoms behaving like one giant superatom, a phenomenon so strange that even Einstein initially doubted its possibility. In this state, rubidium or sodium atoms stop bouncing off each other entirely, instead overlapping like ghostly ripples in a pond. The result, matter that flows without friction, creating bizarre properties like superfluidity, where liquid helium defies gravity to climb up the sides of its container. The methods scientists used to create these conditions would make a science fiction writer jealous. Using precisely tuned lasers, researchers first slow atoms from speeds of several hundred meters per second to just centimeters per second, like hitting the brakes on a race car until it's crawling slower than a snail. Then evaporative cooling takes over, selectively removing the fastest-moving atoms like skimming the hottest soup off the top of a bowl, leaving behind only the coldest. The final temperatures reached are so low they're measured in nanokelvins, billionths of a degree above absolute zero, a realm where quantum effects dominate and particles behave in ways that challenge our understanding of reality itself. What's truly fascinating is how these experiments connect to the wider cosmos. The bizarre behaviors we observe in these ultra-cold labs mirror conditions near black holes or during the universe's first moments, letting physicists test theories about space-time's fabric under controlled conditions. Some researchers even speculate that dark energy, the mysterious force accelerating the universe's expansion, might share properties with the quantum fields observed in these frigid experiments. Every time we push matter closer to absolute zero, we're not just chasing cold, we're uncovering new layers of nature's deepest secrets, proving that sometimes the most extreme conditions reveal the most profound truths. While the universe blazes with stellar infernos and cataclysmic explosions, there's a whisper of cold echoing through every cubic centimeter of space, a relic so pervasive we often overlook it. This is the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, cooling over 13.8 billion years to just 2.7 degrees above absolute zero. That's minus 270.4 degrees Celsius, a temperature so low it makes interstellar space seem warm by comparison. But this isn't just residual chill, it's the oldest light in existence, a snapshot of the universe when it was a mere 380,000 years old, finally cool enough for photons to travel freely. Captured in static-like images from microwave telescopes like Cobe and Planck, this radiation forms a near-perfect thermal blanket across the entire sky. Those iconic speckled maps aren't artistic interpretations, they're literal baby pictures of the cosmos, showing density variations smaller than 1 part in 100,000. These tiny fluctuations, visible as warmer red and cooler blue patches, became the gravitational seeds for all structure in the universe. Every galaxy, every star, even the voids between them owe their existence to these subtle temperature differences frozen in time. The fact that we can detect this radiation at all proves space itself is expanding, stretching those primordial photons from visible light into microwaves over billions of years. Here's where it gets fascinating. The cosmic microwave background isn't just some distant echo. It's all around you right now. About 1% of the static on an untuned analog television comes from these ancient photons, meaning you're literally bathing in Big Bang residue every second. Modern experiments like the South Pole Telescope have measured its temperature so precisely they can detect variations of millionths of a degree, revealing astonishing details about the universe's composition and expansion rate. The European Space Agency's Planck spacecraft mapped this radiation with such sensitivity it could spot temperature differences equivalent to detecting a single warm grain of sand on a beach from orbit. This omnipresent chill tells a remarkable story of cosmic transformation. While the early universe was a roiling plasma 10,000 times hotter than the Sun's surface, relentless expansion has cooled it to barely a whisper above absolute zero. Yet even at this extreme low, the cosmic microwave background carries imprints of titanic forces, sound waves from pressure oscillations in the young cosmos, evidence of dark matter's gravitational pull, and subtle distortions caused by entire galaxy clusters warping space-time. It's the ultimate cold case file, preserving forensic evidence of the universe's birth in the faintest warmth imaginable, a reminder that sometimes the quietest signals carry the loudest truths. The Boomerang Nebula holds a record that makes even the depths of interstellar space seem warm. It's the coldest known natural location in the universe, a ghostly expanse of gas chilling at -272 degrees Celsius. That's just 1 degree above absolute zero, colder than the cosmic microwave background radiation that permeates the void between galaxies. What makes this distant nebula, located 5,000 light-years away, such an extreme cosmic freezer? The answer lies in the death throes of its central star, a red giant shedding its outer layers at breakneck speeds. Picture a star in its final act, ejecting material outward 100 times faster than Earth's fastest winds, so violently that gas expands and cools to temperatures barely above the theoretical limit of cold. This rapid expansion works like the universe's most powerful air conditioner. Just as a can of compressed air feels icy when released, the Boomerang Nebula's gases lose heat as they rush outward at nearly 600,000 kilometers per hour. The result is a nebula shaped like its namesake boomerang, with twin lobes of frigid gas stretching over 3 trillion kilometers, far wider than our solar system. Here's what's truly mind-bending. Human laboratories have actually beaten nature at its own game. While the Boomerang Nebula holds the natural record, scientists on Earth have manipulated atoms to reach temperatures just a billionth of a degree above absolute zero, far colder than anything found in space. The key difference: our artificial cold relies on quantum trickery with lasers and magnetic traps, while the nebula's chill emerges from pure astrophysical forces. Yet both extremes reveal the same truth. When matter approaches absolute zero, the rules of physics warp in extraordinary ways, but nature's method carries an eerie beauty. The Boomerang Nebula's expanding gas doesn't just cool, it creates a light-absorbing shadow effect. Starlight passing through gets partially absorbed by molecules like carbon monoxide, leaving telltale gaps in the spectrum that astronomers use to measure temperature. Recent observations show younger, hotter gas closer to the central star colliding with the frigid outer layers, creating shock waves that glow faintly in millimeter wavelength, like frost forming on a windowpane in slow motion. What this cosmic icebox teaches us goes beyond temperature records. Its existence hints at how stars like our Sun might appear in their final millennia, and how their expelled material eventually seeds new generations of stars and planets. For now, the Boomerang Nebula remains a quiet monument to the universe's ability to extremes, not just in heat, but in cold so profound it defies imagination. Antarctica's vast frozen desert isn't just cold, it's home to temperatures so extreme they turn basic survival into an extreme sport. On July 21, 1983, the Soviet Union's Vostok station registered a bone-shattering -89.2 degrees Celsius, the coldest temperature ever recorded on Earth's surface. That's colder than dry ice, colder than winter nights on Mars, and so frigid that exhaling feels like releasing a cloud of tiny daggers. Your breath crystallizes midair, creating a sparkling mist of ice particles that clatter to the ground like microscopic hail. Even blinking becomes risky. Eyelids can freeze shut in seconds, and exposed skin develops frostbite faster than you can say hypothermia. Surviving these conditions requires more than just warm clothing. It demands engineering as precise as any space mission. Scientists stationed at Vostok live in modular buildings raised on stilts to prevent heat from melting the ice beneath them, which could destabilize the entire structure. Triple-paned windows trap insulating air pockets, while specialized heating systems recapture warmth from exhaust air. Stepping outside means suiting up in layers so thick mobility becomes a challenge. Thermal underwear followed by fleece, down, and finally an outer windproof shell that crackles like cardboard in the cold. Gloves must be thick enough to prevent frostbite yet dexterous enough to handle delicate instruments, a compromise that leaves many researchers with permanently chapped hands despite their precautions. The cold affects everything. Even routine science becomes an act of defiance. Batteries lose 90% of their capacity, fuel turns to jelly, and metal becomes brittle enough to shatter. Helicopters can't fly below -58 degrees Celsius because their hydraulics freeze, leaving the station isolated during the darkest winter months. Yet these hardships reveal astonishing discoveries. Vostok sits above a subglacial lake sealed under 4 kilometers of ice for 15 million years, its waters potentially harboring unknown life forms adapted to extreme conditions. Drilling through the ice sheet requires meticulous care, not just to avoid contamination, but because at these temperatures, a dropped tool or spilled coffee flash freezes into a hazardous obstacle. What's truly remarkable is how human ingenuity adapts. Researchers time outdoor work in short bursts, often communicating via hand signals when face masks freeze solid. They learn to recognize the eerie whisper of the ice, the sound of their own breath crystallizing, a faint tinkling like distant wind chimes, and while the cold is relentless, it also creates surreal beauty. On calm days, temperature inversions make the horizon appear to curve upward, while ice crystals suspended in the air scatter sunlight into halos and phantom suns. These scientists don't just endure Antarctica's extremes, they decode its secrets, proving that even the harshest environments can't extinguish our drive to explore. In this frozen laboratory, every shiver teaches us something new about resilience, both human and planetary. Mars transforms into a frozen wasteland during its polar nights, where temperatures plummet to a staggering -125 degrees Celsius, cold enough to freeze carbon dioxide out of the thin atmosphere into dry ice snow. Unlike Earth's winters, where oceans and thick air help distribute warmth, Mars's bone-chilling cold is amplified by its wispy atmosphere, just 1% as dense as our planet's. This means heat escapes almost instantly into space, leaving the surface to radiate whatever feeble warmth it gathered during the brief daylight hours. NASA Phoenix lander, touching down near the Martian North Pole in 2008, captured this extreme firsthand. Its thermal sensors recorded nighttime temperatures dropping fast enough to watch in real time, like a car's thermometer plunging the moment you drive into deep shadow, but on a planetary scale. The rovers tell an even more vivid story. Images from spacecraft orbiting Mars reveal sprawling dunes blanketed in carbon dioxide frost, their crisp patterns looking more like winter sugar cookies than alien landscapes. When the sun disappears below the horizon for months during polar winter, the already thin air becomes so cold that carbon dioxide, the main component of Mars's atmosphere, condenses directly into ice crystals, creating surreal snowfalls that never melt, only sublimating back into gas when spring returns. This isn't water snow like we know on Earth, it's dry ice falling silently through an atmosphere too thin to carry sound. The rover's weather stations have measured gusts of wind too feeble to feel on Earth, yet in Mars's hyper-cold, low-pressure environment, even these gentle breezes can whip loose dust into towering plumes that stain the polar ice caps with dark streaks. Human explorers would face conditions beyond Antarctic extremes. At these temperatures, a bare hand exposed to Martian air would freeze solid in seconds, not just from the cold, but from the near-vacuum, literally boiling moisture off the skin. Spacesuits would need insulation surpassing anything used on the Moon, while mechanical systems like those on NASA's Perseverance rover rely on radioactive heaters to keep electronics from shattering in the cold. Yet even here, Mars offers surprises. Satellite observations suggest that beneath the ice caps, liquid water might persist in briny underground pockets, kept liquid by dissolved salts that act like antifreeze. It's a reminder that even in the most hostile cold, the universe finds ways to hint at possibilities, hidden oases in a frozen desert, waiting to be discovered. Pluto's famous heart-shaped glacier isn't just a cosmic valentine. It's a sprawling, nitrogen ice wasteland where temperatures nosedive to -240 degrees Celsius, so cold that even the molecules in its frozen plains slow to a near standstill. NASA's New Horizons probe, hurtling past Pluto in 2015, captured this icy heart in stunning detail, revealing a landscape more dynamic than anyone expected. Sputnik Planitia, the glacier's western lobe, stretches over 1,000 kilometers wide, a sheet of solid nitrogen so smooth it reflects sunlight like a cosmic mirror. But here's the twist. This frigid plain isn't just a static slab, it's constantly shifting, flowing like a slow-motion ocean under the pull of Pluto's weak gravity. What makes this glacier so bone-chilling? The answer lies in Pluto's atmosphere, or lack thereof. With surface pressure 100,000 times weaker than Earth's, this dwarf planet can't trap any meaningful heat, allowing temperatures to plummet to some of the lowest in the solar system. The nitrogen ice behaves unlike anything on Earth, sublimating directly from solid to gas under the faint sunlight before recondensing elsewhere in seasonal cycles. New Horizons spotted bizarre polygonal patterns etched into the ice, created by slow convection currents that rise and fall over centuries, like a pot of thick syrup simmering on cosmic low heat. Yet just when you think Pluto is frozen in time, it surprises you. The same spacecraft that mapped Sputnik Planitia's icy stillness also spotted towering geysers spewing nitrogen gas mixed with organic compounds into the thin atmosphere. These cryovolcanic plumes, reaching heights of several kilometers, hint at a subsurface heat source, perhaps radioactive decay or residual warmth from Pluto's formation, turning sections of its interior into a slushy, semi-liquid state. Picture this, a world so cold its surface could freeze air into snow, yet with just enough hidden warmth to occasionally spit that frozen air back into the sky in dramatic eruptions. The contrast couldn't be starker. While one part of Pluto's heart remains locked in a deep freeze older than humanity, other regions seem to whisper of fleeting activity, a reminder that even at the solar system's edge, heat and cold wage an eternal tug of war. These extremes aren't just scientific curiosities, they rewrite the rulebook for what small, distant worlds can do. Every ice crystal in Sputnik Planitia tells a story of a place caught between absolute stillness and surprising change, a cosmic ballet of frost and fire playing out in slow motion. Far beyond the orbits of Neptune and Pluto, in the deepest freeze of our solar system, lies a silent reservoir of ancient ice, the Oort cloud. This hypothetical shell of icy objects stretches nearly a light year from the Sun, where temperatures hover around -250 degrees Celsius, colder than liquid nitrogen, and just 23 degrees above absolute zero. Here, in this perpetual twilight zone, trillions of comets drift in a cosmic deep freeze, preserving pristine ices that have remained unchanged since the solar system's infancy over 4.5 billion years ago. What makes these distant objects so remarkable isn't just their coldness, it's how perfectly this cold acts as a time capsule. Shielded from the sun's warmth and radiation, these icy bodies contain molecular blueprints of the raw materials that once swirled in the protoplanetary disk. While planets and asteroids underwent violent collisions and melting, Oort cloud comets avoided that chaos, staying so far removed that their chemistry remains frozen in time. Imagine stumbling upon a cave where ice has never melted for eons, preserving ancient air bubbles, except in this case, the cave is a vast gravitational net at the solar system's edge, and the trapped gases might include compounds that predate Earth itself. Scientists believe some of these comets are essentially cosmic snowballs, packed not just with water ice but with frozen methane, carbon monoxide, and even complex organic molecules. When occasional gravitational nudges send one plunging toward the inner solar system, the sun's heat vaporizes these ices, creating the spectacular tails we see from Earth. Each visit from an Oort cloud comet, like the famous Hale-Bopp in 1997, is like receiving a postcard from the past, a chance to study ingredients that existed before planets formed. The extreme cold plays another crucial role. It slows chemistry to a crawl. Chemical reactions that would take seconds in a warm lab might require millennia in the Oort cloud's frigid depths. This sluggishness means intricate molecular structures, possibly even probiotic compounds, could survive intact. Some researchers speculate that similar icy bodies delivered water and organic materials to early Earth, seeding our planet with the building blocks of life. Yet studying these distant objects remains a colossal challenge. No spacecraft has ever reached the Oort cloud. Voyager 1, the most distant human-made object, won't enter this region for another 300 years. For now, astronomers rely on telescopic observations and simulations to unravel its secrets. Each time a new long-period comet streaks through the inner solar system, it carries whispers from this frozen frontier, reminding us that the coldest places sometimes hold the hottest clues to our origins. While nature pushes the boundaries of cold in places like the Boomerang Nebula, human ingenuity has taken temperature extremes into uncharted territory. In a Massachusetts laboratory, MIT physicists have performed what seems like scientific alchemy, cooling atoms to -273.144 degrees Celsius, just a whisper above absolute zero. At this unimaginable chill, mere millionths of a degree from the coldest possible temperature, matter stops behaving by everyday rules and enters a quantum wonderland where particles move in synchronized waves and liquids flow uphill. The secret lies in a dazzling choreography of lasers and magnetic fields. Researchers start by trapping sodium or rubidium atoms in a vacuum chamber, then hit them with precisely tuned laser beams that act like a kind of optical molasses. These lasers are adjusted to frequencies that make photons strike atoms head-on, slowing their motion much like throwing tennis balls at a moving truck would gradually break it to a halt. Once the atoms are crawling along at centimeters per second, slower than a drifting snowflake, an intricate dance of magnetic fields takes over, forcing the atoms into an ever tighter crowd while allowing the most energetic ones to escape like skimming steam off a pot of soup. The remaining atoms, now huddled in the coldest conditions ever created by humans, begin exhibiting behaviors straight out of science fiction. One such phenomenon is superfluidity, where chilled helium or ultra-cold gases lose all viscosity. Picture a liquid creeping up the sides of its container in defiance of gravity, or swirling endlessly without losing energy to friction, a perfect fluid with zero resistance. Even stranger are time crystals, structures that repeat not in space like ordinary crystals, but in time, oscillating between states without any energy input. Imagine a pendulum that keeps swinging forever without being pushed, or a snowflake whose pattern changes predictably every few seconds. These aren't just laboratory curiosities, they hint at new phases of matter that could revolutionize quantum computing. What makes these experiments so groundbreaking is how they blur the line between microscopic and macroscopic worlds. In everyday life, quantum weirdness hides beneath layers of thermal noise, but near absolute zero, these bizarre effects become visible to the naked eye. Atoms stretched into wave-like states span millimeters, allowing scientists to directly observe quantum entanglement. the spooky connection Einstein famously doubted on scales large enough to photograph. Some experiments have even created quantum tornadoes, where thousands of atoms rotate in perfect unison like a celestial dance frozen in liquid light. By pushing matter to these extremes, physicists aren't just breaking records, they're stress testing the very laws of nature. Conditions this cold simulate the bizarre physics near black holes or the universe's first moments after the Big Bang. Every time researchers nudge atoms closer to absolute zero, they uncover new layers of quantum reality, proving that sometimes, to glimpse the universe's deepest secrets, you have to cool things down until time itself seems to stand still. Slowing atoms to a near standstill takes more than just turning down the universe's thermostat. It requires something straight out of a sci-fi novel, optical molasses. Picture a swarm of superheated atoms moving chaotically at thousands of kilometers per hour, then suddenly being caught in a web of laser beams meticulously tuned to act like cosmic glue. This is the essence of laser cooling, a technique so ingenious it earned its pioneers the 1997 Nobel Prize in Physics. By exploiting the subtle push of photons, particles of light, scientists can essentially choreograph a subatomic ballet where atoms lose momentum with every laser strike until they're creeping along slower than a snail's pace. The magic happens in stainless steel vacuum chambers smaller than a shoebox, where rubidium or sodium atoms are first isolated from any stray heat. 6 laser beams arranged in opposing pairs along the X, Y, and Z axes create a 3-dimensional interference pattern that acts like a viscous syrup for atoms. Each time an atom moves toward one of these lasers, the Doppler effect shifts the light's frequency from the atom's perspective, increasing the likelihood it will absorb a photon. The subsequent recoil from this absorption slows the atom's motion, like throwing a baseball against the direction of a moving car to break it. Repeat this process millions of times per second, and those once frenetic atoms eventually crawl to temperatures just millionths of a degree above absolute zero. What makes this Nobel-winning technique revolutionary isn't just the cold it achieves, it's the precision. Earlier cooling methods could only chill atoms to around -270 degrees Celsius, but optical molasses shattered that barrier, reaching temperatures colder than interstellar space. The key breakthrough came with the realization that lasers could be tuned to target specific atomic transitions, turning each photon into a perfectly calibrated speed bump. Researchers like Stephen Chu, Claude Cohen-Tanauji, and William D. Phillips refined this approach, adding magnetic fields to further corral the atoms into what's known as a magneto-optical trap. Modern setups resemble high-tech snow globes, where glowing clouds of ultra-cold atoms hover like ethereal fog, contained by forces no thicker than a razor's edge. But the real marvel happens when you peer beyond the hardware. Suspended in that frigid cloud, atoms start behaving like waves rather than particles, their quantum nature laid bare. This isn't just laboratory spectacle, it's the foundation of atomic clocks guiding GPS satellites, quantum sensors detecting subterranean mineral deposits, and upcoming quantum computers that could crack problems impossible for classical machines. Every flicker of light in those laser beams isn't just cooling atoms, it's freezing time itself into perfect, measurable increments, proving that sometimes the universe's deepest secrets hide in the quietest, coldest corners. Space isn't just cold, it's a thermal roller coaster where sunlight and shadow create blistering extremes inches apart. While sci-fi loves to portray space as uniformly freezing, the reality is far more dramatic. Take the International Space Station. One side bakes at a scorching 120 degrees Celsius under unfiltered sunlight, hot enough to boil water instantly in Earth's atmosphere, while the opposite side plunges to -160 degrees in shade, colder than winter nights on Mars. This violent swing happens not because space itself has temperature, but because there's no air to distribute heat, just pure, unfiltered radiation carving the universe into pockets of inferno and ice. This paradox stems from how heat moves in a vacuum. On Earth, warmth spreads through conduction, touching a hot pan, or convection, hot air rising, but space lacks molecules to carry that energy. Instead, objects exchange heat solely through thermal radiation, the same invisible infrared waves you feel from a campfire. Without atmosphere to buffer these extremes, surfaces exposed to sunlight absorb every photon's energy, like a black car seat left in summer glare. Meanwhile, shaded areas radiate their heat unchecked into the void, cooling rapidly like a steak pulled from a grill. The Moon exemplifies this. Its daytime rocks reach 127 degrees, while nighttime craters bottom out at -173, a 300-degree swing without an atmosphere to temper it. Managing these extremes is a nightmare for spacecraft engineers. The ISS uses gold-coated reflector panels and rotating radiators to balance temperatures, while astronaut suits have 14 layers of insulation to prevent freezing or roasting during spacewalks. Even the Hubble Space Telescope's mirrors were designed to expand and contract without warping as they cycle between sunlight and shadow every 90 minutes. Failure to account for these swings can be catastrophic. When Apollo 13's cabin lost heating, condensation froze to the walls, nearly drowning the crew in floating ice crystals. What's truly mind-bending is how these conditions affect materials differently. Metal joints on satellites can weld themselves together in sunlight from atomic diffusion, then become brittle as glass in shadow. Solar panels must generate power while enduring daily cycles that would shatter ordinary glass. Recent experiments even suggest asteroid surfaces may crack like desert mud under these thermal stresses, creating the gravelly regolith seen by sample return missions. So the next time someone calls space cold, remember, it's not the void that's freezing or burning, but the objects within it, caught in an eternal tug of war between radiation and the absence of anything to share the heat with. Out here, temperature isn't just a number, it's a matter of life, death, and engineering ingenuity. When astronauts return from space, their spacecraft must survive one of nature's most violent temperature extremes. A fiery plunge through Earth's atmosphere that turns the air itself into a searing plasma hotter than lava. During re-entry, friction between the speeding capsule and atmospheric molecules generates temperatures reaching 1,650 degrees Celsius, hot enough to melt steel beams like candle wax. This isn't just heat, it's a blistering inferno that would vaporize most materials in seconds. Yet every crew that's ever returned home, from Mercury to SpaceX's Dragon, has relied on an ingenious thermal protection system to survive this gauntlet. The secret lies in materials that don't just resist heat but transform it. Spacecraft shields use ablative coatings, layers of resin-packed fibers that deliberately char and erode under extreme temperatures. As the outer surface burns away, it carries heat with it, creating a protective boundary layer that insulates the craft underneath. NASA Apollo capsules took this to the extreme, with heat shields so thick they lost nearly a third of their mass during re-entry. Picture a cosmic pencil eraser, sacrificing itself stroke by stroke to keep astronauts safe. Modern spacecraft like Orion use advanced variants called Avcoat, a honeycomb structure filled with epoxy that chars predictably, ensuring no single spot overheats. But ablative shields aren't the only solution. The Space Shuttle's belly was armored with over 20,000 silica tiles, each custom cut to fit like a ceramic jigsaw puzzle. These tiles could withstand 1,500 degrees Celsius while remaining cool enough to touch on the underside, a property so counterintuitive engineers famously demonstrated it by holding a freshly heated tile with bare hands during press conferences. Their magic came from being 94% air, making them lighter than styrofoam yet capable of absorbing tremendous heat. Columbia's tragic loss in 2003 tragically proved how crucial even one damaged tile could be. Today's material scientists are pushing boundaries further. SpaceX's Starship uses hexagonal tiles of stainless steel alloyed with chromium and nickel, reflecting heat rather than absorbing it. Meanwhile, NASA experiments with ultra-high-temperature ceramics like zirconium diboride that remain solid at over 3,000 degrees. Some prototypes even incorporate microscopic pores that sweat cooling gases when heated, mimicking human skin's cooling mechanism. Each innovation reflects a deeper truth: surviving re-entry isn't about fighting physics, but dancing with it, using every trick in the thermal playbook to turn an unavoidable firestorm into a survivable homecoming. What's often overlooked is how these shields must also endure extreme cold. While one side bakes at re-entry temperatures, the opposite face faces the -150-degree chill of space, a thermal whiplash that stresses materials in ways no Earthbound test can fully replicate. Next-gen designs may borrow from nature, mimicking the heat-resistant proteins found in deep-sea vent microbes or the insulating structure of Arctic animal fur. Every returning spacecraft carries not just astronauts, but the collective genius of chemists, physicists, and engineers who have turned an impossible temperature barrier into a temporary inconvenience on the road home. Brown dwarfs are cosmic misfits, too massive to be planets yet too small to be true stars, forever trapped in stellar puberty. These failed stars smolder at around 2,000 degrees Celsius, a temperature that sounds extreme until you compare it to the sun's furnace-like core. Infrared telescopes reveal them as faint, ember-like objects glowing stubbornly in the darkness, never quite mustering the heat needed to kickstart full-scale hydrogen fusion. Imagine a bonfire that never catches properly, stuck in a permanent state of flickering without ever bursting into full flame. That's the fate of every brown dwarf in the universe. What keeps these objects in thermal limbo? It all comes down to mass. While a star like our Sun has enough gravitational heft to squeeze its core to 15 million degrees, the threshold for sustained hydrogen fusion, brown dwarfs top out at about 8% of the Sun's mass. That's just shy of the critical pressure needed to ignite the nuclear fires that define true stars. Instead, they briefly burn deuterium, a heavy isotope of hydrogen, during their youth, generating fleeting warmth before settling into a slow, eternal cool-down. Over billions of years, their faint glow dims until they become little more than cold, invisible husks drifting through space. Infrared images from observatories like NASA's Spitzer Space Telescope paint a haunting portrait of these objects. Unlike stars that blaze with visible light, brown dwarfs emit most of their energy in invisible infrared wavelengths, appearing as ghostly purple or magenta smudges against the blackness of space. Some even have violent weather systems, clouds of molten iron and silicate droplets churned by hurricane-force winds, with storms so vast they could swallow Earth whole. The closest known brown dwarf, Lumen 16, just 6.5 light-years away, exhibits atmospheric turbulence that would put Jupiter's Great Red Spot to shame, yet its surface temperature is no hotter than freshly poured lava. The tragedy of brown dwarfs is their near-miss nature. Had they accumulated just a bit more gas during their formation, they might have crossed the threshold into stardom, lighting up their corner of the galaxy. Instead, they serve as cosmic cautionary tales, reminders that in the universe, the difference between a blazing sun and a fading cinder can come down to a few percentage points of mass. Yet their very existence helps astronomers draw the line between planets and stars, proving that nature doesn't always follow tidy categories. These perpetual almost stars may not shine brightly, but they glow just enough to teach us how fragile the balance is between celestial fire and cosmic obscurity. Kepler 78b isn't just another exoplanet. It's a cosmic cauldron where entire oceans don't just shimmer with heat, they rage in perpetual, incandescent fury. This lava world, orbiting dangerously close to its star, boasts surface temperatures around 3,000 degrees Celsius, hot enough to vaporize iron, boil rock into an atmosphere of molten silica, and turn what should be solid ground into a global magma hurricane. Imagine standing on a shoreline where waves aren't made of water, but of liquid basalt taller than skyscrapers, crashing under a sky glowing like the inside of a blast furnace. That's Kepler-78b's everyday reality. The planet's extreme heat comes from its absurdly tight orbit, completing a full revolution around its star in just 8.5 hours. At this distance, gravitational forces stretch and knead Kepler-78b's interior like cosmic taffy, generating immense tidal friction that adds to the star's relentless radiation. Infrared observations suggest its dayside is a single, roiling ocean of superheated lava, while the night side, if you can call it that, might host rivers of molten metal flowing beneath a crust that constantly cracks and reforms under the strain. The temperature difference between these hemispheres likely generates supersonic winds, carrying vaporized rock from the scorching dayside to the slightly cooler night side, where it condenses into rock rain before being swept back in a vicious cycle. But here's what makes Kepler-78b truly terrifying. It's spiraling toward its doom. Precise measurements of its orbit reveal the planet is drifting closer to its star by about 2 centimeters every year, a death march that will see it ripped apart by stellar gravity in roughly 3 billion years. Right now, that slow-motion destruction manifests as constant volcanic upheaval, with tidal forces flexing the planet's crust so violently that eruptions may span entire continents. Some astrophysicists compare it to pouring water into hot oil the planet's surface can't stabilize, so it keeps erupting in a relentless planet-wide tantrum. The cruel irony, Kepler-78b is almost exactly Earth's size and mass, a rocky twin born under a cosmic curse. Where our planet orbits in a temperate sweet spot, this doppelganger circles hellishly close, showing just how fine the line is between habitable paradise and molten nightmare. Future telescopes might detect similar worlds glowing like embers in the darkness, each a cautionary tale written in lava, proof that in the universe, even twins can grow up in wildly different environments, with one destined for blue oceans and green forests, and the other for endless burning oceans of fire. Among the cosmic graveyard of dead stars, white dwarfs glow with a quiet but intense finality, stellar embers packing the mass of a sun into an Earth-sized package, their cores simmering at 100,000 degrees Celsius. These aren't just hot objects, they're crystallized remnants of stars like our own, squeezed into degenerate matter so dense that a sugar cube-sized chunk would weigh as much as an elephant. Hubble's sharp eye has captured their ethereal glow in ultraviolet and visible light, revealing surfaces hotter than laboratory plasma, yet paradoxically too dim to see with the naked eye from neighboring star systems. What keeps these collapsed cores from vanishing into black holes? The answer lies in one of quantum mechanics' most defiant rules, the Pauli exclusion principle. At these extremes, electrons get crammed so tightly together that they can't occupy the same quantum states, creating an outward pressure called electron degeneracy. Picture an overstuffed subway car where no more passengers can squeeze in except here. The passengers are subatomic particles, and the car is the crushing gravitational weight of a dead star. This quantum standoff halts the white dwarf's collapse, freezing it in a bizarre state where increasing mass actually shrinks the star further. The most massive white dwarfs approach a critical limit called the Chandrasekhar limit, about 1.4 times the Sun's mass, where even electron degeneracy can't hold back gravity's pull, triggering a catastrophic collapse into a neutron star or black hole. Hubble's images reveal another haunting feature. Many white dwarfs are encircled by ghostly disks of vaporized planets. When a star like the Sun dies, it swells into a red giant, incinerating or swallowing nearby worlds before shedding its outer layers. The surviving core, now a white dwarf, sometimes cannibalizes the shattered remains of its former planetary system. Spectroscopy has detected heavy elements like calcium, iron, and even oxygen polluting these dead stars' atmospheres, chemical tombstones marking worlds that once were. In a macabre twist, some white dwarfs may have diamond cores, their carbon crystallizing under unimaginable pressures over billions of years, a celestial funeral gem forged from stellar ashes. Time behaves strangely around these cosmic relics. A white dwarf's searing heat leaks away so slowly that the oldest ones in the universe have cooled to just a few thousand degrees, still far hotter than lava, but barely luminous enough to spot. The universe isn't old enough for any white dwarf to have fully cooled into a black dwarf, a hypothetical cold, dark cinder. Until then, these stellar tombstones keep vigil, dimming, yes, but still whispering tales of fusions in game through their blistering surfaces and the quantum defiance that keeps them from vanishing entirely. Every one we find is a preview of our sun's distant future, a blazing postscript to the story of starlight. Some stars don't just drift through the cosmos, they get violently evicted from their galaxies at speeds topping 3 million kilometers per hour, leaving behind tails of superheated gas glowing at 50,000 degrees Celsius. These hypervelocity stars are cosmic fugitives, flung into the void by gravitational slingshots from supermassive black holes. Picture a stellar pinball game where the flipper is the crushing gravity well of a black hole, hurling stars so fast they escape their home galaxies entirely. The result is a breathtaking spectacle, streaks of ionized hydrogen and helium trailing behind them like interstellar comets, heated to temperatures rivaling the sun's corona by sheer friction with the sparse gas between galaxies. How does a black hole fling a star like this? It starts with a dance of doom. When a binary star system, two stars orbiting each other, wanders too close to a galaxy's central black hole, one star gets captured while the other is ejected at mind-bending speeds. The energy stolen from the black hole's rotation propels the survivor outward like a stone from a sling, accelerating it to up to 1% of light speed. These runaway stars don't just fade quietly into the darkness. As they barrel through the thin plasma of intergalactic space, their motion rams into stray atoms, compressing and heating the gas into glowing shockwaves visible in ultraviolet light. Telescopes like Hubble have spotted dozens of these blazing trails, some stretching tens of light years behind their fleeing stars. The irony is delicious. The same force that pulls everything inexorably inward, the black hole's gravity, also serves as the universe's ultimate catapult. The fastest known hypervelocity star, designated S5HVS1, rockets through space at over 2,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in just 6 minutes. At that speed, its tail isn't just hot. It's a fluorescent scar across the cosmos, a testament to forces violent enough to kick a star clean out of its galactic neighborhood. What's truly humbling is realizing these stars aren't rare accidents. Simulations suggest every large galaxy might eject hundreds over its lifetime, meaning the darkness between galaxies isn't entirely empty. It's littered with these radiant outcasts, their searing tails fading slowly as they voyage into the abyss. Each one carries a story written in light and velocity, a reminder that even stars aren't immune to the universe's capricious whims. And somewhere out there, another black hole is lining up its next gravitational shot, preparing to launch yet another stellar fugitive into the endless night. Gamma-ray bursts are nature's most violent tantrums, cosmic detonations so powerful they outshine entire galaxies for seconds, leaving behind a wake of gas heated to 1 billion degrees Celsius. Picture the energy of 1,000 suns unleashed in less time than it takes to blink, superheating interstellar material until electrons are torn from atoms, creating a soup of plasma hotter than the core of any star. These beams of pure gamma radiation, traveling at light speed, can sterilize entire star systems in their path, baking any unfortunate planet with enough radiation to strip away atmospheres and boil oceans in moments. The mechanics behind this extreme heat reveal just how terrifying these events truly are. When a massive star collapses into a black hole or neutron stars merge, they fire twin jets of energy narrower than a pencil beam but stretching billions of light years. The initial flash lasts mere seconds, but the aftermath, called the afterglow, occurs when these jets plow into surrounding gas, creating shock waves that heat material to temperatures rivaling the early universe's first minutes. This isn't just a brief spike. The superheated plasma can persist for days, radiating X-rays and visible light detectable across the cosmos. What makes gamma-ray bursts particularly unsettling is their reach. If one occurred within a few thousand light-years of Earth, the afterglow's ultraviolet radiation could trigger chemical reactions in our atmosphere, depleting the ozone layer and exposing life to deadly solar radiation for years. Paleontologists even speculate that a nearby burst might have contributed to the Ordovician mass extinction 450 million years ago, when 60% of marine species vanished without clear cause. Modern satellites like Swift and Fermi constantly scan the skies for these events, not just for science, but as an early warning system for a threat that could arrive without notice. Yet in their destructive power lies a cosmic irony. Gamma-ray bursts might also seed the universe with heavy elements. The same extreme temperatures that vaporize worlds also forge gold, platinum, and uranium through rapid neutron capture, scattering these materials across galaxies. Every time we detect a burst's afterglow, we're watching the universe's most destructive force double as an unwitting alchemist, turning annihilation into creation under temperatures so extreme they redefine the limits of physics itself. Deep beneath the French countryside, scientists are building an artificial star, a colossal machine designed to contain plasma hotter than the sun's core at 150 million degrees Celsius. This is ITER, the world's largest nuclear fusion experiment, a 35-nation effort to bottle the power of stars in a donut-shaped chamber called a tokamak. The temperatures inside defy imagination, 10 times hotter than the sun's center, hot enough to vaporize any known material instantly. But here's the twist: this plasma won't melt its container because it never actually touches the walls. Instead, it floats suspended in midair by the invisible force of magnetic fields stronger than an MRI machine's, dancing in a vacuum like a fiery ghost trapped in a cage of pure physics. Creating this stellar inferno starts with hydrogen isotopes, deuterium and tritium, heated until electrons tear free from atoms, forming a superhot ionized gas. The real magic happens when these charged particles collide with enough force to overcome their natural repulsion, fusing into helium and releasing tremendous energy. In stars, gravity provides the crushing pressure needed for fusion, but on Earth, we must simulate stellar conditions through intense heat and precision magnetic confinement. The plasma in ITER chamber will spiral along magnetic field lines like cars on a racetrack, kept precisely centered away from the walls by 16,000 tons of superconducting magnets cooled to -269 degrees, creating perhaps the most extreme temperature gradient in human engineering. Yet containing this artificial star is like trying to hold lightning in a bottle. Plasma is inherently unstable, prone to developing kinks and whirls that can break magnetic containment in milliseconds. When disruptions occur, the results are spectacular. ITER predecessor, JET, once produced a plasma burst so powerful it melted its own tungsten tiles despite only running for seconds. Modern tokamaks use real-time supercomputers to predict and correct plasma instabilities faster than the blink of an eye, adjusting magnetic fields thousands of times per second to maintain balance. Some experimental reactors even employ liquid lithium walls that self-heal from plasma damage, mimicking the regenerative properties of living tissue. The payoff for mastering this delicate dance could be revolutionary. 1 kilogram of fusion fuel contains the energy of 10 million kilograms of fossil fuels without long-lived radioactive waste or greenhouse gases. ITER aims to produce 10 times more power than it consumes, paving the way for commercial reactors that might one day harness star power here on Earth. Already, private companies are testing innovative alternatives: compact spherical tokamaks, laser-ignited fusion capsules, and even reactor designs inspired by the natural stability of plasma in lightning bolts. Each approach shares the same breathtaking ambition: to recreate, however briefly, the cosmic fires that light the universe, proving that the most extreme temperatures in existence aren't just destructive forces, they might be the key to humanity's clean energy future. Neptune and Uranus hide a dazzling secret deep beneath their icy clouds, torrential rains of diamonds, forged in atmospheres so extreme they turn methane into glittering carbon crystals. Deep inside these ice giants, where pressures reach millions of times Earth's surface level and temperatures soar past 7,000 degrees, scientists believe solid diamond hailstones form and sink toward the cores like cosmic gemstones in a celestial storm. This isn't science fiction. Lab experiments have recreated these alien conditions, proving that the same methane that fuels stovetops here on Earth transforms into precious gems under the crushing weight of planetary atmospheres. The process starts with methane, a molecule consisting of one carbon atom bonded to 4 hydrogens. In Neptune's upper atmosphere, fierce lightning storms rip these molecules apart, releasing carbon atoms that get dragged downward by the planet's intense gravity. As they descend, pressures mount to staggering levels, first compressing the carbon into graphite, then further squeezing it into crystalline diamond structures. Picture this: a blizzard of gems the size of icebergs, slowly sinking through layers of superheated water and ammonia thousands of kilometers thick, eventually piling up around the planet's rocky core in a diamond-encrusted layer. Scientists at SLAC National Accelerator Laboratory proved this phenomenon was possible by recreating Neptune's interior in miniature. Using high-powered lasers, they blasted a plastic film resembling methane's composition, generating shock waves that mimic the pressure of an ice giant's atmosphere. In nanoseconds, the carbon atoms within the plastic rearranged into microscopic diamonds, confirming what astrophysicists had theorized for decades. Follow-up experiments in Germany took it further, using intense X-rays to watch the transformation in real time, capturing how diamonds form and then immediately get swallowed by swirling currents of dense, ionized matter. The implications stretch beyond planetary science. Understanding diamond rain helps explain why Neptune and Uranus radiate more heat than they receive from the Sun. The friction of diamond crystals sinking through dense material may generate internal warmth. Some models even suggest these planets could have entire layers of liquid diamond near their cores, with carbon behaving like metal under such extremes, conducting electricity and creating exotic magnetic fields. What makes this discovery truly mind-bending is the scale. Neptune's diamond storms likely produce millions of tons of gems annually, far more than humanity has ever mined. Yet these diamonds aren't the clear-cut stones of jewelry. They're likely partially dissolved in the planet's slushy interior, mixed with other elements until they resemble something closer to a carbon-rich magma. So while we'll never mine these distant treasures, they remind us that the universe's most beautiful phenomena often exist in its most hostile environments, where pressure and heat conspire to turn the mundane into the magnificent. Kelt 9b isn't just a scorching exoplanet, it's a cosmic anomaly where the word extreme doesn't begin to cover it. Orbiting perilously close to its blue-hot host star, this planet endures surface temperatures of 4,300 degrees Celsius, making it hotter than many red dwarf stars. To put that into perspective, that's nearly twice as hot as lava and only about 1,000 degrees cooler than the surface of our own sun. But here's what makes Kelt 9b truly bizarre. Its atmosphere isn't just hot, it's literally evaporating into space, leaving behind a glittering tail of vaporized metals like iron and titanium that stretch millions of kilometers like a comet burning up in slow motion. The cause of this planetary meltdown is a brutal combination of proximity and stellar fury. Kelt 9b's host star, Kelt 9, is a rare type of star that burns at almost 10,000 degrees Celsius, bombarding the planet with ultraviolet radiation so intense it strips atoms apart. Locked in a death spiral just 3 million miles from its star, closer than Mercury orbits our Sun, the planet completes a full orbit in less than 36 hours. Gravitational forces have tidally locked it, meaning one side forever faces the star in perpetual, blistering daylight, while the other stares into the freezing void of space. The temperature difference between these hemispheres creates supersonic winds that scream across the planet at over 60,000 kilometers per hour, carrying vaporized metal from the day side to the night side, where it condenses into metallic rain only to be vaporized again in an endless, hellish cycle. What's even more astonishing is how Kelt 9b defies conventional planetary science. Most gas giants like Jupiter form far from their stars where ices and gases can accumulate. But Kelt 9b somehow either migrated inward or formed in this infernal zone, leaving astronomers puzzled. Its extreme heat has puffed it up to nearly twice Jupiter's size despite having only half the mass, giving it the density of styrofoam. Spectroscopic observations reveal its atmosphere isn't just losing hydrogen. It's shedding heavier elements like magnesium and silicon, creating a transient cloud of ionized gas around it. Some scientists speculate that given enough time, the entire planet might evaporate, leaving behind nothing but a ghostly ring of vaporized rock where a world once orbited. For now, Kelt 9b serves as a stark reminder of the universe's capacity for extremes, a place where a planet blurs the line between celestial body and stellar companion, where molten iron falls as rain, and where the very concept of surface dissolves into a seething, escaping haze. It challenges our definitions, proving that somewhere out there, nature is always cooking up conditions more outrageous than anything we could invent. Rewind the cosmic clock to the universe's very first second, a mere heartbeat after the Big Bang, and you'd find conditions so extreme they make today's supernova and neutron stars seem lukewarm. The temperature during that primordial instant, a number so vast it defies everyday comprehension, 100 million trillion degrees Celsius. That's a 1 followed by 32 zeros, a heat so intense it didn't just melt atoms, it prevented them from existing at all. Instead, the infant universe seethed with a searing, featureless soup of quarks and gluons, the fundamental particles that would later bind together to form protons and neutrons. This quark-gluon plasma was the universe's first and most exotic state of matter, a perfect liquid with zero viscosity, where particles moved freely without resistance. In this primordial inferno, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were still unified as a single, all-encompassing superforce. Space itself expanded faster than light could traverse it, doubling in size at least 90 times within a fraction of a second during cosmic inflation. The sheer energy density was so extreme that empty vacuum fluctuations birthed pairs of particles and antiparticles that annihilated each other just as quickly, filling the cosmos with a deafening roar of virtual creation and destruction. Scientists at CERN Large Hadron Collider have recreated microscopic glimpses of this primordial firestorm. By smashing lead nuclei together at 99.99% the speed of light, they've generated fleeting quark-gluon plasma droplets no wider than an atom, yet reaching temperatures of 5.5 trillion degrees, over 300,000 times hotter than the Sun's core. These experiments reveal a bizarre liquid that flows more perfectly than water, with quarks so liberated they forget their inherent properties like up or down, behaving instead like a collective superfluid. Detectors surrounding the collisions capture the aftermath particle jets spraying outward in patterns that betray the plasma's near-zero friction, mirroring conditions that last existed universally some 13.8 billion years ago. What's truly humbling is how these experiments connect to the cosmos we see today. As the universe expanded and cooled past that first unimaginable second, quarks and gluons finally froze into protons and neutrons, the building blocks of all visible matter. The slight excess of matter over antimatter during this era, just one extra quark per billion annihilations, became every star, planet, and living creature in existence. CERN recreations aren't just about breaking records, they're cosmic archaeology, probing the moment when the universe's very rules were written. Every collision briefly resurrects a time when heat and energy ruled absolutely, before structure and form could even be imagined, a reminder that everything we know emerged from the most extreme conditions reality has ever produced. From the universe's first unimaginable moments, a seething ocean of quark soup hotter than 100 million trillion degrees, to the eerie, near-motionless chill of the Boomerang Nebula just 1 degree above absolute zero, we've journeyed through the cosmos' most staggering temperature extremes. Heat and cold aren't just measurements, they're the invisible sculptors of reality itself. Supernova forge the very elements in your bones at 1 billion degrees, while the faint whispers of the cosmic microwave background, a mere whisper above absolute zero, carry echoes of the Big Bang. On distant exoplanets, iron rains from incandescent skies, while neutron stars glow with surfaces so hot a teaspoon of their material could power civilizations. Temperature doesn't just define environments, it dictates the fate of galaxies, the birth of stars, and even the possibility of life. Without the violent heat of stellar cores, there'd be no carbon for DNA. Without the icy depths of interstellar space, molecules could never clump into planets. Every extreme we've explored today, from the sun-scorched plains of Venus to the evaporating atmosphere of Kelt 9b, reveals a universe constantly reinventing itself through the push and pull of heat and cold. So, what's the most mind-bending space fact you've ever heard? Maybe it's the diamond rains of Neptune, the time crystals forming in labs near absolute zero, or the fact that you're literally breathing stardust forged in a supernova's heart. Drop your favorites in the comments. We're obsessed with the wild, untamed physics of the cosmos, and we bet you are too. If this journey through the universe's most extreme temperatures blew your mind like a gamma-ray burst, smash that like button and subscribe for more deep dives into the chaos and wonder of space. Until next time, keep looking up and remember, the universe isn't just stranger than we imagine, it's stranger than we can.